Hi everyone at Medical Sciences by Naphtali Muhumuza. We want to talk about the principles of determination of cardiac markers. In the previous video, we have looked at the interpretation of cardiac markers, but we want to see how are they determined in the lab. Which principles are behind? We don't normally give you procedures because procedures are always per manufacturer's mind. So we always refer to the manufacturer. And always remember to subscribe if you haven't subscribed, share your comments and like the video. And among the cardiac markers we listed in the previous video, we saw there are those which are enzymes. And among the enzymes, we listed total CK, which comprised of different isoenzymes. We looked at LDH, we looked at AST. But AST is already covered under LFTs. So here we shall look at LDH and CK. And specifically, we shall look at the determination of total creatine kinase. Then under the proteins, though the enzymes are also protein in nature, but these are not enzymes, we shall look at myoglobin and troponin. And these myoglobin and troponin, we shall see their determination using sandwich ELISA. We shall use sandwich ELISA, quantitative method. Then these ones we shall use kinetic methods to determine. These enzymes are going to use kinetic methods, whereas this one is sandwich ELISA. And without delay, we are going to begin with total CK. So we want to look at determination, the principle of determination of total creatine kinase. Total CK, how is it determined in the lab? And we are using kinetic method, meaning we are going to monitor continuously. And this kinetic method, we know that in muscles, that is both skeletal and cardiac, we see creatine kinase catalyzing the phosphorylation of creatine to phosphocreatine. But in this case, we are doing the reverse, that whenever we have phosphocreatine or creatine phosphate, we have creatine phosphate or phosphocreatine So when we have creatine phosphate in muscles, we see it being dephosphorylated. It undergoes dephosphorylation, meaning we are removing a phosphate group. It is dephosphorylated, meaning we are removing a phosphate inorganic. And after removing it, this one is happening in the presence of creatine kinase enzyme. Creatine kinase enzyme is catalyzing the dephosphorylation or the removal of phosphate group from creatine phosphate to form creatine. The result is formation of creatine. And this one we are going to see there is utilization of ADP and we are forming ATP. So we are removing the phosphate group from the creatine phosphate, adding it to ADP to produce ATP. So in these products, we are interested in ATP being produced, which is adenosine triphosphate in this reaction. Then the ATP produced in the reaction is reacted with glucose. And we know in the presence of glucose in muscles, we have an enzyme hexokinase. We have hexokinase enzyme, which adds a phosphate group from ATP on glucose at carbon number 6, forming glucose 6-phosphate. And the enzyme that catalyzes this reaction in the muscles is hexokinase. And this hexokinase utilizes ATP and produces ADP plus phosphate inorganic. And this one, it occurs in presence of magnesium ion as a cofactor, whereby this hexokinase catalyzes dephosphorylation. So this reaction is phosphorylation. The other one was dephosphorylation. This is phosphorylation because we are adding a phosphate group at carbon number 6 of glucose to form glucose 6-phosphate plus ADP. But in this reaction, we are interested in the formation of glucose 6-phosphate. That glucose 6-phosphate formed, it is oxidized, it undergoes oxidation to form 6-phosphogluconolactone. Phosphogluconolactone. And this 6-phosphogluconolactone formed, it is the oxidation occurs in the presence of NADP, whereby when we have nicotinamide adenine dinucleotide phosphate, for it is reduced to NADP-H. NADP-H. And whenever I see presence of NAD ecoenzyme, I think of a dehydrogenase enzyme, and this dehydrogenase enzyme is glucose 6-phosphate dehydrogenase. So glucose 6-phosphate dehydrogenase is catalyzing the oxidation of glucose 6-phosphate to form 6-phosphogluconolactone with the concomitant production of NADP-H. So what we are interested in is the production of NADP-H, which we are going to monitor continuously. And we shall say, we said it is a kinetic method, so meaning when we produce NADP-H, we are going to see that the rate of formation of NADP-H produced is monitored continuously. At 340 nanometer wavelength. We use wavelength of 340 spectrophotometrically. We use a spectrophotometer. We are using a spectrophotometer to monitor the rate of formation of NADP-H. Is monitored at this wavelength, and the intensity is directly proportional. No, the rate, here we don't say the intensity, we say the rate of formation of NADP-H is directly proportional. Is directly proportional to amount of CK in the sample, to amount of creatine kinase in the sample. So this is the principle where we can use to determine total creatine kinase in the sample in case we are suspecting myocardial infarction. That we have reagent containing creatine phosphate which is dephosphorylated, and this creatine phosphate, the reagent contains it and is dephosphorylated by removing a phosphate inorganic in the presence of creatine kinase to form creatine with the production of ATP. And the ATP produced reacts with glucose at carbon number 6 and adds the phosphate group, forming glucose 6-phosphate with the production of ADP. And the enzyme that catalyzes this reaction is hexokinase in the presence of magnesium as a cofactor. But after producing glucose 6-phosphate, it is oxidized. This reaction is oxidation reaction. It is oxidized, whereby glucose 6-phosphate dehydrogenase enzyme catalyzes the oxidation of glucose 6-phosphate to form 6-phosphogluconolactone with the concomitant or with the production of NADP-H. And this NADP-H produced is the one that we monitor continuously at a fixed time interval at a 340 nanometer spectrophotometrically. And the rate of formation of NADP-H, the more we produce NADP-H, it means there is more CK in the sample. So the more the production of NADH, the more the creatine kinase in the sample. So that is how we can determine creatine kinase. And after understanding this, we shall see that the reference range of total CK, its reference range for men, we see it ranging from 35 to 174 or 75 international units per liter. This is the major reference range of total CK. This is for total creatine kinase. So whenever someone has beyond 175, we can suspect myocardial infarction, the way we saw the interpretation in the previous video. So the second enzyme that we can see its principle is LDH. We want to see the principle of LDH. How do we determine lactate dehydrogenase in the lab? But for the isoenzymes, from isoenzyme 1 up to 5, we said we can always separate them by protein electrophoresis. But in the lab, we are using kinetic method, whereby if we have lactate, the reagent lactate, and we can easily convert it to pyruvate. This conversion of pyruvate requires this LDH enzyme, that is lactate dehydrogenase, so lactate is reduced to pyruvate. Lactate is reduced to pyruvate, whereby the NAD plus is reduced to NADH. So this is also an oxidation. It is not a reduction reaction. We are seeing we are oxidizing. Lactate is oxidized to pyruvate. It is a reversible reaction. We can even also convert pyruvate back to lactate. And this one, lactate, is always formed whenever during glycolysis and anaerobic respiration, we see pyruvate being converted to lactate, which is a 3-carbon sugar. So we are saying if the reagent contains lactate, the sample having lactate dehydrogenase, the lactate dehydrogenase catalyzes the oxidation of lactate. We are saying LDH catalyzes the oxidation or the conversion of lactate to pyruvate with the production of NADH. And what we are interested in is production of NADH. The NADH which is being produced is the one that we are going to monitor continuously, like the way we have done it here, whereby the rate of formation of NADH, rate of formation or rate of production of NADH is monitored continuously. Monitored continuously at a fixed time interval at 340 nanometer wavelength spectrophotometrically. So we are using a spectrophotometer at 340 nanometer wavelength, and the rate of this formation, the more we produce NADH, the more the LDH in the sample. So the rate of its production is directly proportional. It's directly proportional to the amount of LDH in the blood sample. So this is how we are determining. And it is very important to always tell us that it is directly proportional. Never forget that. It is directly proportional. So this is the method, the kinetic method we are using to measure the presence or to quantify the amount of LDH in the blood sample of our patient utilizing the production of NADH in the presence of LDH, catalyzing the oxidation of lactate. So this is the principle we are using to quantify our LDH. So this is the method we can use. But for different isoenzymes, the way we saw in the previous video, we use protein electrophoresis, which I have already discussed in one of my videos. So if you want to understand how we can separate different isoenzymes of LDH, you can visit my video on protein electrophoresis and be able to understand. So these are the enzymes. We said this one is covered under lefties, so we shall see it both kinetic method and endpoint method by Reitman and Franken. So the next we are going to discuss in this video is myoglobin and troponin, and you are going to allow me to tackle them at once because they are using the same method, whereby we are going to use a sandwich ELISA to quantify them. So we want to look at the determination of the principle of determination of troponin stroke myoglobin. I want to put them together, and we are saying by sandwich ELISA. By sandwich ELISA. In the previous video, we saw troponin has troponin I, troponin T, and troponin C. And we said troponin I is more specific, followed by troponin T, but troponin C is not specific to the cardiac. And we are using solid phase ELISA, what we call sandwich ELISA. That if I have a microtiter well, this microtiter well is pre-coated with monoclonal, specific monoclonal antibodies. If it is troponin, if we can use the example of troponin in this case, we're going to see that the microtiter well, this microtiter well is pre-coated with troponin antibody, what we call anti-troponin monoclonal antibody. So we have it already with pre-coated monoclonal. So what we do, our role is to add the sample. We come and add our sample. And what is in the sample? This sample contains troponin antigens. And these troponin antigens in the sample, they are specific to this anti-troponin monoclonal antibodies, pre-coated in the microtiter well. So when they are added, during intubation, we see this microtiter well, which is already pre-coated with the monoclonal troponin and monoclonal troponin antibody. In case the sample contains the antigens, so the sample is containing these antigens come and bind to the paratopes using their epitopes to the monoclonal troponin and troponin monoclonal antibody. And some of them, if they are in excess, some of them will not get where to bind. So after the intubation as a per manufacturer, sometimes we intubate for 30 minutes at room temperature. After intubation, we are intubating to allow these antigens to bind to the antibody to form antibody-antigen complex or antigen-antibody complex. And because there is excess, it is followed by washing. We wash with the buffer to remove excess. So we wash to remove the excess antigens, troponin antigens, or myoglobin antigen. After washing, we shall remain with only, by these are the troponin monoclonal, then we remain only with the ones which are binding, these antigens that are binding, which have formed the antigen antibody complex. So the essence of washing was to remove the excess. After washing, we add a substrate, before a substrate, we add enzyme linked, or we had labeled anti-troponin or antimyoglobin antibody, which is monoclonal, and we intubate. And during that intubation, in case there was, because of the presence of the antigens, we are going to see these labeled, enzyme labeled, or enzyme linked anti-troponin antibodies binding to the epitopes of these troponin antigens. So if we have the pre-coated biochlorotiter well, we have already the antigens of the troponin binding, we have them binding. So, and we have added enzyme linked monoclonal anti-protroponin enzyme linked. They come and bind, but they are added in excess. So some will not get where to bind. And those which are excess, which have nowhere to bind. So we are seeing on addition of enzyme linked anti-troponin antibody, they bind together, and we find that the antigen, the troponin antigen, is sandwiched in between the unlabeled antibody, monoclonal antibody, with the enzyme linked, or what we call labeled monoclonal antibody. So during intubation, we are saying that the antigen is sandwiched. Troponin antigen is sandwiched in between. It is like the way we see chapati, man. Like these people who bake sandwiches or chapatis who make Rolex here in Uganda. We are going to see that the frampen is acting as a microtiter well, and the first chapati is the pre-coated monoclonal antibody. And then when you add an egg in between, the egg becomes the antigen, which is specific to the antibody. Then we normally add another second chapati, and the egg is always sandwiched in between. And this egg, after being sandwiched in between, that is what we are calling sandwich ELISA. So this sandwich ELISA, the way we are seeing, this is the first egg, this is the first chapati, the egg, and then the second chapati. So we see the two chapatis sandwiching the egg in between, what we are calling the antigen, troponin antigen, then the anti-troponin unlabeled, then this is labeled troponin antibody, sandwiching the antigen from the patient sample in between. After this, we wash. It is followed by washing. And why are we washing? Is to remove excess and bound, enzyme labeled antibodies, enzyme labeled monoclonal antibodies. These which never got where to bind, we wash and we remove. And when we remove them, we remain with this. Remain with this. We see these guys being sandwiched in between. Then we have added the labeled. So the essence of washing was to remove the unbound enzyme labeled or enzyme linked antibody, which are specific. So after getting this sandwich, now these enzymes, and the major enzyme we are using is HRP, horseradish peroxidase. So this enzyme we are using to link is horseradish peroxidase. So this horseradish peroxidase, which is the enzyme that is linked on the monoclonal antibody, it needs a substrate. So the next step is we add the substrate. And this substrate we normally use majorly TMB, whereby TMB is known as tetramethylbenzene. Tetramethylbenzene is the substrate. Why are we adding a substrate? Is that this enzyme is to catalyze to form a product. So the enzyme HRP catalyzes this substrate in the presence of HRP to form a yellow colored product. It forms a yellow colored product during incubation for 30 minutes or sometimes by the time specified by the manufacturer. So when we add a substrate and we incubate, the host radish peroxidase catalyzes or breaks down the substrate, that is TMB, tetramethylbenzene, to form a yellow colored product. And this yellow colored product, after 30 minutes, it is terminated by addition of a stop solution. So after 30 minutes of incubation, forming a yellow colored product, we now add a stop solution. We add a stop solution, and the stop solution commonly used is 1 normal sulfuric acid. Is the one used as a stop solution, and this stop solution leads to the change of the color from yellow to blue colored solution. And this blue colored solution, after addition of the stop solution to stop the reaction, is the one that is determined spectrophotometrically at 450 nanometer wavelength. We use 450 nanometer wavelength, and the intensity. So we are using this 450 nanometer wavelength, and the intensity of the blue color is directly proportional to the amount of troponin or myoglobin in the sample. So this is the same procedure for both using sandwich ELISA. If we are looking for troponin, we always put troponin. If we are using myoglobin, we say antibody, we say myoglobin antibody, or we say antigen, myoglobin antigen. So we use specific antibodies, but the procedure is the same, whereby we have pre-coated microtiter wave. We are adding a sample containing antigens which bind to the paratopes. Then we wash to remove the excess. After washing, we add the enzyme-linked antibody and we intubate. During intubation, they react and they sandwich the antigen in between. Then it is followed by washing to remove the unbound. And after washing, we add a substrate, that is TMB, whereby HRP will catalyze it to form a yellow colored solution. And the yellow colored solution after incubation of 30 minutes is terminated by addition of a stop solution known as 1 normal sulfuric acid, leading to the change of the color from yellow to blue. And then it is the blue color formed is determined spectrophotometrically at 540 nanometer wavelength, and the intensity of the blue color formed here is directly proportional to the amount of either troponin antigen in the sample or myoglobin antigen in the sample. That is how we can determine using sandwich ELISA. And sometimes qualitatively, we are using also rapid strips, which are utilizing the same, whereby these strips have the test pad and the control pad, whereby the test pad is immobilized with monoclonal antibody. Then on the sample pad, if I have a strip like this for qualitative, we're saying for qualitative methods, we are having a strip. On this strip, it has a sample pad. This is the sample pad. So this is a qualitative method, not quantitative. but employing ELISA. And after this sample pad, after this where we apply a sample, we have also the test line and the control line. So this is the test line and the control line. This is the strip. So what we do, that this sample pad is, we find in the sample pad, it is conjugated with enzyme linked antibody. So whenever you come and add a sample, if the sample contains the antigen, this antigen reacts with the enzyme linked antibody and they move together by capillarity. We will see them moving by capillarity towards the test region. And remember, this test region is immobilized with monoclonal antibodies, gold monoclonal antibodies or colloidal. These ones in the sample pad area, they are conjugated with the enzyme, but these ones in the sample area, they are unlabeled. So they are always immobilized. So they are immobilized in the test area. So whenever this sample with the enzyme linked antibody, the sample containing the antigen with the enzyme linked, they are moving by capillarity towards the test area. Whenever they find there this unlabeled antibody, they are captured, and when they are captured, they lead to formation of the pink color. So the pink we see when it is positive, the pink to red color form is formed showing positive. Then it continues moving and also it reacts with the control area. And this one, control area, is to confirm that the strip is working. So still we can improvise by using this qualitative method, still employing this ELISA. The difference is that this one we are not quantifying using spectrum photometer, but we are just reading positive or negative. So this is how we can always determine our myoglobin and troponin, either using qualitative strip method or using sandwich ELISA, whereby it is quantitative. Thank you so much for listening. Always remember to subscribe, share your comments, and like the video so that we can continue to learn more and more. Thank you so much.